Yeah, good morning to one and all. This is Nagajyoti working as an assistant professor in Department of EC in St. Peter's Engineering College. So in this session, I want to discuss about error detecting and correcting codes. So here, the name itself indicates error. So the complete error detection and correction process is used where we are using a communication in terms of zeros and ones. So here if we are using a communication process of encoding and decoding process, there we are getting a concept of error correction and detection. So in case whenever we are saying a term called as a communication, so here communication is nothing but a transfer of information from transmitting end to that of the receiving end. So here transmitting end is nothing but from where we are sending our actual information or from where we are sending our information, starting point of an information is nothing but called as a transmitter. Similarly, at which point we are receiving our information is called as a receiver. So here, in case of a communication, whenever we are transmitting our information along with our original information, we are going to transmit some other bits. So here, error itself indicates the transmitter bits are not is equivalent to receiver bits. We are not equal to is nothing but it is not specifying the number of bits. It is specifying whatever the data which is present at the transmitter end should be same towards the receiver end. If the transmitted bits are not is equivalent or is not same as that of the receiver bits, then we can say that the error has been occurred. So here detection itself indicates finding out the error is nothing but called as error detection. Similarly, after finding out an error, we need to correct the error. So here in case of an error detection and correction process, first we are finding out where the error is present, then we are saying how to overcome that error by using a process called as correction process. So in case of an error detection and correction process, along with our original information, that is along with the message bits, I'll be adding some extra bits to the message bits. These extra bits are called as parity bits. So here whenever we are saying error detection and correction along with the message bits, along with our original information, we are adding some other bits. Those extra bits are nothing but called as a parity bits. As we have already discussed what is meant by parity and what are the different types of parities. That is, parity bits are extra bits which are added along with the message bits in order to detect and correct the error. These parity bits may be even parity or odd parity. That is, in case of message bits, if the number of ones are odd, if we append a parity bit as 0, then it is called as an odd parity. Now let me take here message bits. I am assuming that the message bits are 3 message bits. Those are A, B and C. And here a parity bit. I am first assuming that it is a odd parity. Next I am assuming it as an even parity. And whatever the word which we are getting after this addition, it is nothing but called as a code word. So here A, B, C. If we are using 3 variables, we will be getting 2 power 3 combinations which is equivalent to 8. That is from 0 to 7. So I am just taking random numbers of 3 as an example. So here 0, 0, 0. So in case of 0, 0, 0, the number of ones are 0. If I want to make this message bits as an odd parity message bits, I need to add 1 in the parity bit. Because if you are taking all these 4 bits, the total number of ones present in this code word is 1. If there is 1, that itself indicates odd. So here parity bits are nothing but which represents an extra bit which is added along with the original information. So, if the same bit I want to convert into an even parity, I need to append a 0 because the total number of ones should be even. So, here if you are combining these, it is nothing but called as a code word. But it is not a compulsion that we need to append a parity bit at the last. There is some procedure where to append the parity bits. In general, that is in case of a Hamming code which we are discussing now, always the parity bits should be added in the powers of 2. So here, just for an example, I am saying that if the number of ones are already odd, if it is an odd parity, I need to append a 0. If the number of ones are zeros, if I want to make use of an odd parity, I need to append a 1. Similarly, in this case, 1, 0, 1. So the total number of ones are 2. If I want to make it as an odd parity, the total number of ones should be odd. So, if I am adding 1, the total number of ones are 3, which are nothing but odd parity bits. Similarly, for the same number, if I want to make use of an even parity, already there are 2 ones in the given message. So, I need to append a 0 in the even parity. Similarly, for the last combination, which is equivalent to triple 1, the total number of ones are odd. So, if I want to make use of an odd parity, the parity bit should be equivalent to 0. If I want to make triple 1 as an even parity, I want to make as 4 ones. That is the reason I want to add a 1 over here. So this is all about the what is meant by a parity bit, what is the importance of a parity bit. Now let us see this with one example. So here I am assuming that using an even parity, find which words contain an error. That is, the question is, we need to find an error, find which words contain error using parity bit. Here I am assuming that using even parity. So here, in this case, I am assuming that the first given number is 1 0 1 0 1 0 1 0. So here this is a code word which is given in the question. What we need to do is we need to find out whether the error is present or not, assuming that it has even parity. So here even itself indicates the total number of ones in the given code word should be equal to even number of ones. So in this code word, the total number of ones are 4. Number of ones are 4. So here 4 is nothing but an even number. So whatever the code word which we received is nothing but a correct code word. That itself indicates there is no error in this code word. Similarly, let me take other more examples. triple one zero 1011. So in this case, I am having 7 ones. That is triple one 01011. So the total number of ones are 7. But in the given question, they have given it as even parity. Even parity itself indicates the number of ones should be even. But here the number of ones are odd. That itself indicates this code word is not a correct code word. Represents there is some error present in the code word. So by using a parity bits, just we can able to find out whether the error is present or not. But we cannot able to detect where the error is present and how to correct the error. So the drawback of these parity bits are it is basically used in order to find out whether the error is present or not. But even we cannot able to find out where that particular error is present. That is, we can able to identify the error, presence of error, but we cannot able to find out where the exact error is present. So in order to overcome the drawback of these parity bits, we are going for the next most concept called as Hamming code. So the importance of this Hamming code is used in order to detect the error. That is not only saying whether the error is present or not, it is used in order to find out where the exact location of an error is present, and we can also able to correct the error by using a Hamming code. Now let us see the importance of a Hamming code and how to generate a code word as well as how to correct a code word. So in case of a Hamming code, this Hamming code concept consists of two different categories. The first one is, first we should know how to generation of a code word. That is, we'll be having a message bits. From that message bits, we need to add a parity bits and we need to generate a code word. So here this generation of a code word will be done at the transmitter side of a communication system. And the second part is, after generating the code word, we need to transmit that code word to the receiver part, and from the receiver part we should able to detect the error, then we should able to correct the error. So here the first step is, that is the first category is how to generate a code word. This generation of a code word is done at the transmitter side. Once we know how to generate a code word, the transmitted code word is sent towards the receiver side. From the receiver, that is, the transmitted data should be, we need to check whether the transmitted data is equivalent to received data or not. So here the second part is finding out the error as well as correction of an error. That is error detection as well as error correction. Now let us see the first thing, which is nothing but how to generate a code word. That is generation of a code word. So in case of a generation of a code word, the first thing is, let me start explaining with an example. So here I am assuming that I am having 4-bit message bits. So here 4-bit message bits itself indicates. So the question here is, encode the binary word, encode the binary word 1011 into 7 bit into a 7-bit having code, assuming it as an even parity. So here I want to assume this as the parity as even parity. So here in the given question, encode itself indicates whatever the data which they have given is nothing but a message bits. So here the first one is in the given question they have given 4 bits. Those 4 bits are 1011. But they have asked to convert these 4 bits into a 7 bits. So here the first step is we need to find out how many number of parity bits are required. So the step 1 is find number of parity bits required. So the condition for finding out the number of parity bits required is nothing but 2 power p greater than or equal to x plus p plus 1. Here either you can take x or m. Here x or represents the message bits and p represents the parity bits. So the first step is we need to find out the number of parity bits required. The number of parity bits required are 2 power p greater than or equal to x plus p plus 1. And whatever this condition which we are saying, it should satisfy at least minimum of equal to. So here in order to find out the number of parity bits required, we need to do it in the trial and error method. That is, here the number of message bits in the given question are 4. So 2 power p greater than or equal to 4 plus p plus 1. That is 2 power p greater than or equal to 5 plus p. Let the minimum value of p is always starts from 1. That is, there should be a minimum of 1 parity bit. So, if let p is equivalent to 1. If p is equivalent to 1, 2 power 1 is 2. 2 is not greater than or equal to 6. So, if the p value is equivalent to 1, it is not satisfying the condition. Similarly, if p is equivalent to 2, 2 square is 4. 4 is also not greater than or equal to 7. 5 plus 2 is 7. So, if we take p value is equivalent to 3, 2 power 3 greater than or equal to 5 plus p, that is 8 greater than or equal to 8, as it is satisfying the minimum condition, that itself indicates here the value of p is equivalent to 3. So here the number of parity bits required for 4-bit message bits are 3. So here the value, if there are message bits are, if the message bits are 4, the parity bit should be equivalent to 3. So, if you add these message bits with the parity bits, the total code word is nothing but total is 7. That is the reason in the question they have specified it as 7 bits. So, here code word is nothing but message bits followed by the parity bits is called as a code word. So, if the message is having 4 bits, the parity bits required for 4 message bits are 3, which are nothing but total are 7. Now, let us go for the step 2. So, in case of the step 2, we need to remember where to place the parity bits. That is, always parity bit should be placed in powers of 2. Always parity bits should be placed in powers of 2. That is, as here I am having 3 parity bits. The position of parity bits are 2 power 0, 2 power 1, 2 square. That is at first position, second position and the fourth position. So then step 2 is here we need to place the parity bits in the powers of 2. The next one is we need to write down a tabular column in such a way that bit designation. So here this table is called as bit location table. This is called as bit location table. In case of a bit location table, we'll be having the terms as bit designation, bit location, message bits or information bits, or the last one is parity bits. So here in case of this table, we need to fill the details of all these in such a way that here the bit designation itself indicates. Here we need to specifically find out the corresponding bit is whether the message bit or the parity bit. So let us see these things over here. So here bit location itself indicates the total number of bits, that is message bits are 4 and the parity bits are 3, which are nothing but total number of bits are 7. So under the bit location we need to write down the numbers from 1 to 7. So next, bit designation itself indicates we need to write down whether that is the message bits or the parity bits. And the other more important thing is under the bit location itself, here if we observe this example, the highest number is 7. So the 7 equivalent in terms of the binary is 111. So here under the bit location only, here I am writing the equivalent of that corresponding bit, which is equivalent to 7. Similarly, for 6, the corresponding binary bit is 110. For 5, 101. For 4, 100. For 3, 011. For 2, 010. For 1, 001. At least you should be in a position to write down the binary equivalents from 0 to 15 directly without converting each and every, that is without doing any division process. You must be able to tell the direct numbers from 0 to 15 at least. So here just as I have already told you, in case always the parity bits are placed in the powers of 2, that is 2 power 0 is 1. So here this is a parity bit, 2 power 1 is 2, this is a parity bit, and 2 square is 4, this is the third parity bit. So here P represents the parity bits. So the parity bits are placed in the powers of 2, that is 1, 2 and 4, and the remaining bits are called as data bits. So here the remaining bits are data bits. Here this is data bit, this is also data bit, this is also data bit, this is data bit. So instead of representing as D1, D2, D3, D4, just I am representing in a manner in such a way that this is first data bit position, second data bit, third data bit and the fourth data bit positions. So in the given question, this is the first data bit, that is LSB always represents the first data bit position and MSB represents the highest data bit position. So here That is, in the first D1 position, I am writing it as 1. Second D2 is also 1. D3 is 0. D4 is 1. So from the given question itself, we can directly write down the message bits in the corresponding positions. Coming to parity bits representation. In the given question, as I have specifically mentioned it as, the type of parity is even parity. So in case of an even parity, we need to go for, in order to write down the parity bits, I need to go for the next step, that is, I need to assign the values to the parity bits. That is, step 3 is assigning values to parity bits. So in case of an assigning values to the parity bits, now let us check for P1. For P1, if you observe the binary equivalent of the P1, 1 is present at the least significant bit. So check for which numbers we are having 1 in the least significant bit position. So here for P1, that is for 1, I am having the 1 at the least significant. So 1. But in case of 2, 1 is present in the middle, but I want to check 1 only for the least significant. So for, in order to write down for P1, I will be getting 1, 3. In case of 3, I am having 1 in the LSB position. So for P1, 1, 3, 4 is having for the LSB, but I want to check only for the LSB. So if you observe this complete second row, I will be getting 1 at the LSB bit only for 1, 3, 5, 7. So I am writing for P1, 1, 3, 5, 7. Now if you observe, do you have any message bit under the 1? No. So write down this 1, leave this 1 as a blank. Under 3 bit location, what is the corresponding bit which we are having? 1. Under 5, that is under the bit location of 5, we are having the bit as 1. Under 7, we are having the bit as 1. So, I will be getting 3 ones and the other one is P1. So, here 3 ones itself indicates it is which parity? It is odd parity. But in the question, they have mentioned it as even parity. So, if I want to convert this odd parity into an even parity, I want to make this P1 to 1. If I make P1 to 1, I am getting 4 ones, which is nothing but equivalent to even parity. That is the reason here I am writing P1 is equivalent to 1. So the value of the P1 is what? 1. Similarly, if I want to check for P2, under P2, where the 1 is present, the 1 is present in the middle position. So, in order to check for P2, what I need to do? Here, for P2, I need to check which bits? 2, 3, 6, 7. So in order to write down for P2, I need to check for 2, 3, 6 and 7. Do you have any number under the P2? No. So keep it as a blank. What is the number which we are having at the third location? 1. Under 6, 0. Under 7, 1. So in this one, we are having the total number of ones are 2, which is nothing but even number of ones or even parity of ones. So I need to add a 0 in terms of P2. So here the value of P2 should be equivalent to 0 because I want to make use of it as an even parity. So P2 is equivalent to 0. Now let us see with P3. So whenever we are saying for P3, the one is present at the MSB. So for the remaining, that is for 4, 5, 6, 7. The ones are present in the MSB bits for the bit locations of 4, 5, 6 and 7. Under 4 there is blank. So I can keep a dash mark over here. And for 5, 6, 7 I'm having 1, 0, 1. So the total number of ones are even number of ones. The given question is also having even parity. So I need to add 0 for the P3. So I have assigned the values for P1, P2 and P3 and remaining data bits write down as it is. Now the total code word is, this is nothing but a parity bit. That is just we are placing a parities in this position, and the last step is we need to write down a code word. So here the total code word for this 1011 is just add those, that is write down the same. The D4 bit is 1, D3 bit is 0, D2 bit is 1, followed by parity bit 0. Next is D1 bit which is equivalent to 1. Next is parity bit 0. Next is parity bit 1. So this is a complete code word for the given question of 1011. Similarly, if I ask for the same message bits, instead of assuming it as an even parity, if I want to make use of an odd parity, the only change which we will be getting is wherever you got P1 as 1, now you will be getting P1 as 0 and P2 as 1. That is wherever you got 1, that 1 will be replaced with 0, 0 will be replaced with 1 only for the parity bits, because we are not finding out any data bits. Already the data bits are given in the question, just we are finding out the values of the parity bits. So just we need to find out how many number of ones are present. So in order to find out those, the important step over here is how we are writing this 1357. That is, this 1357 is based on where the one is present in that particular bit location. This is how to generate a code word for a given data word of an Hamming code. Now let us see the next step, that is nothing but how to detect and how to correct an error. So before going this, just I'll summarize this generation of a code word. That is, the step 1 is we need to find out how many number of parity bits are required. So the formula for finding out the parity bits required is 2 power p greater than or equal to x plus p plus 1. The second step is we need to place the parity bits in the powers of 2. And in step 2, we need to write down a bit location table which specifies what is the designation of the bit, what is the location of the bit, which are the parity bits and which are the information bits. After this, the step 3 is we need to write down assigning of the values for the parity bits. After assigning the values of the parity bits, combinedly write down all those in a single one which represents what is a complete code word for the given question. Now let us see the second one, which is nothing but how to find out where the error is present in the given code. So here The other more important thing is whatever the formula which we have used, that is 2 power p greater than or equal to x plus p plus 1 is valid in order to detect a single error, that is single error detection and correction is possible by using this formula. Now let us see the second way, that is how to detect the error and how to correct the error. So in case of a detection and correction of an error, I am assuming that the given, that is the complete code word which they have given is, instead of giving it as a message bits, now they will be giving it as a code word. So here the complete code word is having, that is the transmitted code word is 0110011. So here the transmitted code word is 0110011 and the received code word is different from that of the transmitted code word, and here they are asking to find out, this is a code word, you need to detect and correct single error detection and correction, assuming it as even parity. So here if I am assuming it as an even parity, the only change which I can do over here is the total bits are 7. So assuming it as even parity. So for the second type of method, what we need to do is directly we need to write down bit location table. So here, as I have already told you, in case of a bit location table, we are having bit designation, bit location. The little bit change in this table is, here we are not mentioning it as message bits and parity bits. I am directly writing the received code word. So the first one is bit designation, bit location, binary location, and the next one is code word. So here the total number of bits, that is total bits given in the question are 7. So in case of a bit designation, I will be having the complete bits of 7. So here in case of a bit designation, just I will be writing which are the message bits and which are the parity bits. So bit location is total are 7 bits. As we have discussed that parity bits are always placed in the powers of 2. This is first parity bit, second parity bit, third parity bit, and the remaining are data bits. Here binary location is nothing but equivalent of the binary bits which we have done previously. And in the code word, here we need to write down the complete code word which is given. That is 0, 1, 1, 0, 0, 1, 1. So in order to find out where the error is present, we need to use of the bits which are nothing but the parity bits. So in case of a parity bits, that is here the parity bits are P1. So the associated bits with the P1. So here the P1 similar to that of the previous one. So in case of a P1, that is 1 is present in the least significant bit. So we need to check where the 1 is present for the least significant bit. So it is related with 1, 3, 5, 7. That is 1, 3, 5, 7. And write down what are the corresponding bits which we are having under 1357. So under 1 I am having a bit of 1. For 3, 0. For 5, 1. For 7, 0. Here, in order to find out where the error is present or not, we can do this in two different methods. The first method is, so here I will be getting the number as 1, 3, 5 and 7. So here under 1, 3, 5 and under 1, 3, 5 and 7 I will be getting here. So here the given question is even parity. So here the total number of ones in 1, 3, 5, 7 is also even. That represents there is no error related towards the P1. Similarly, now let me check for P2. For P2, the 1 is present in the middle position. So I need to check for 2, 3, 6, 7. 2, 3, 6 and 7. For 2, the corresponding number is 1. For 3, 0. For 6, 1. For 7, 0. So the total number of ones are even. The given question is also even. That represents for P2 also there is no error. Similarly, we need to check for P3. For P3, the one is present at the MSB bit, which is nothing but 4, 5, 6, 7. So for checking for P3, I need to check for 4, 5, 6 and 7 bits. Under 4, I am having 0. For 5, 1. For 6, 1. For 7, 0. So the total number of ones are even. The given question is also having even parity. That itself indicates no error. So as P1, P2, P3, all these are no errors. That itself indicates the transmitted code word is same as that of the received code word. So in this we can say that there is no error between the transmitted and received code word. Now let us see the same example with a little bit change in one position. So here I am assuming it as even parity only, but the change in the code word is instead of having the number as 0, 1, 1, 00, 1, I am assuming that now the transmitted code, that is the received code word is 0, 1, 0, 1, 0, 1. So this complete, the first three rows will be the same. The only change over here is now the received code word is 0, 1. Now this becomes 0. 0, 1, 0, 0, 1. For P1, I need to check the same 1, 3, 5 and 7. So under 1 now I am having 1. For 3, 0. But for 5, here I am having 0. So now I need to replace this 1 with 0. Now in this, the change over here which we can able to see over here is the only change in this is now the total number of ones are odd, but in the given question the parity shift is equivalent to even. So if I want to convert this odd parity into an even parity, I need to make use of an adding other more bit. Or the other way which I can perform is just perform the XOR operation for all these cases. That is 1 XOR with 0, 1. 1 XOR with 0, 1. Or in simple words, if the odd number of ones are there, the output of this should be is equivalent to 1. So, this is the one way. Or the other way is, if the given question parity is not matching with these parity bits, we can say that there is an error at the corresponding position. So, here itself indicates this is an odd parity, but the given question is even parity. That itself indicates there is an error. Similarly, check for 2, 3, 6 and 7 for P2. So here the 2 is 1, 3 is 0, 6 is 1, 7 is 0. The total number of ones are even. The given question is also even. As it is same, there is no error for the P2. Coming for the P3, 4, 5, 6, 7. For 4 it is 0, for 5, 0, for 6, 1, for 7, 0. So here the total number of ones are odd, but the given question is even parity, as it is not matching with the parity bits which we got and we got of the question. It represents there is an error. So now we can conclude that there is an error in the P1 and P3. So now we got the error is present, but we need to find out what is the exact location of an error present in the given code word. So in order to write down the exact location of the code word present in this, the thing over here is just write down the corresponding bits in such a way that first is P1, P2, P3. So here the P1 value is nothing but 1. So the P1 is 1, P2 is 1, P3 is also 1. So here what we need to find out, how can we find out where the error is present itself indicates there is an error at the P1 bit as well as at the P3 bit. So what is the corresponding error is nothing but just perform the XOR operation. 1 XOR with 0, that is the total number of, in this complete, how many number of ones are there? 1. So whenever we are performing XOR operation for the odd number of ones, the resultant is equivalent to 1. So P1 is 1. Similarly, if you perform even number of ones for the XOR operation, P2 is equivalent to 0. Or in simple words, I can say that odd number of ones is 1, even number of ones is 0. Here also odd number of ones are there. So P3 is equivalent to 1. So here P1 is 1, P2 is 0, P3 is 1. P1 is 1, P2 is 0, P3 is 1. Always write down from the LSB towards the LSB. That itself indicates the equivalent for 101 in terms of the decimal is 5. That itself indicates the error is present in the fifth position. So here fifth position itself indicates this is the fifth position. So the error is present in the fifth position as we are having only two digits which are nothing but zeros and ones. Wherever 0 is there, replace with 1. Wherever 1 is there, replace with the 0. So the correct code word is 0, 1, 1, double 0, double 1. So this is the way how to find out where the error is present and how to correct that error by using an Hamming code.